All right. So, good morning, everyone. Let's start because it's 6 minutes over. Yeah. So, we were discussing about cache in our last lectures, and we have discussed memory hierarchy. We know cache and main memory are integrated in terms of their operation with respect to each other, and cache operates upon the principle of locality. We can have temporal locality, we can have spatial locality. Temporal is based upon time, and spatial is based upon the location of data items and instructions in the cache. Right now, uh, I think after studying all these concepts, we need to start doing some numericals based upon this so that we actually are able to implement the learned basics in our day-to-day problems as well. So I guess I started last time with one numerical. This one we did on last Saturday. Yeah, this one also we did in the last class, I think. We'll do one more today. All right. So, yes, write down this question, everyone. It's a very simple question. So this says, in a 34-bit microprocessor, we have a 16 kilobyte cache. Just a minute. Yes, so we have this 16 kilobyte cache which is direct mapped and it has a 64 byte block size. How many bits of address will be required for the tag, index, and the offset? So we need to calculate now. Anyone who can tell me how will we start? It's a very simple question. Can you hear me? Will I get an acknowledgement? Are you all able to hear me properly? No. ओह तो बड़ी प्रॉब्लम है तो ज्वाइन ही नहीं हुआ अब तक. हाँ जी रिया. गुड मॉर्निंग. आवाज नहीं आ रही है क्लास में? अरे मैं तो पढ़ा रही हूँ. अच्छा. और ये ज्वाइनिंग लिखा आ रहा है पर ज्वाइन नहीं हुए स्टूडेंट्स. माय गॉड. नहीं नहीं, एडमिट ऑल तो मैंने बड़ी देर का किया है. वहाँ ज्वाइनिंग लिखा आ रहा है. हाँ, एक बार दोबारा ज्वाइन करो. और मैं तो अपने आप को पढ़ा रही हूँ, फिर मैं तो ध्यान ही नहीं दिया. चलो ठीक है, करो ज्वाइन करो. ये इंटरनेट की प्रॉब्लम है मुझे लगता है. मेरा तो मसा ही चला है बट वहाँ ज्वाइनिंग लिखा आ रहा है. स्टूडेंट ज्वाइन नहीं हो पा रहे. ये इसका फुल आ रहा है सिग्नल. इसको थोड़ा ऊपर रखो फिर, या बाहर रख दो निकाल के. मीना चलेगी? फिर से आएगी? नहीं नहीं, ऑफ करके ऑन मत करो. ये बड़ी प्रॉब्लम है. मैं रीस्टार्ट करती हूँ क्लास एक बार, है ना? हाँ जी, हो रहा है ज्वाइन?
Yes, ma'am.
हो गया. पीपल आर एबल टू हियर मी. आई एम गेटिंग एक्नॉलेजमेंट. चलो ठीक है. आई हैव 77 पार्टिसिपेंट्स एंड आई हैव एडमिटेड ऑल. होपफुली सबका ज्वाइन होना चाहिए. ठीक है, ओके. Yeah, I think there was some network issues. So I guess I was teaching just myself. I had started my class at 45. Chalo koi na, I am sharing the screen again and we'll start it again, okay? No problem. Connectivity issues are always there. Yeah. So last time we did some basic, uh, concepts about memory hierarchy and the integration of cache with the main memory, right? So we all know the read-write policies of cache. Any address that comes from the processor for the cache is a physical address. So depending upon the main memory size, the cache addressing bits are designed or they are configured, right? I'll just keep writing all the side by side because we have to use it now. So your physical address that comes from the processor is dependent on the main memory size, right? Any address that comes from the processor obviously will go to the first hierarchical level in the memory, which is cache. And cache has its own addressing, which is tag followed by index followed by the offset. There was one very important bit in the cache called the valid bit. What was it?
Ma'am,
It
it
shows
indicates
whether there is some data in cache or no.
Yes. So for the first go, when power is turned from off to the on state, this will not, the valid bit will be zero because cache will be empty. And this is just to identify to the processor that no address mapping is required anymore. Do not waste your time on address mapping, right? So this valid bit is one bit data, can be one, can be zero. When the cache blocks are empty, it will be zero, and once they have some data, this will be one, right? And the address mapping, how does it take place? Anyone? What is the first thing that matches?
index.
Yes. So the first thing that matches is the index followed by your tag
Um,
after checking your valid bit. So, and then your
Offset.
offset. Yeah. So offset is concatenated along to get the data out of the respective block. Then, um, if the address matches, it's a cache hit. If the address does not match, it is a cache miss. I'm talking about the read policy. So a read hit and a read miss. And what happens on a read miss? What happens on a read miss? Anyone?
Then it
That address is searched in the next level of.
Very good. So in the lower level of memory hierarchy, which is the main memory, the respective address is looked for, and after getting the data from there, based upon locality, a copy of it is created in the cache depending upon what type of cache it is. So I can either have placement policy, or I can have a replacement policy, and both depend upon what kind of cache we are using. So a placement policy and replacement policy can depend upon whether the cache is your fully associative or it is set associative or it is your direct mapped, right? Okay, one thing I want to let you know, last lecture maybe there was some network issue, could not be recorded. So whatever is available, I'll be uploading by today evening. Maybe I don't know whether this will also get recorded or not. There is some problem with Zoom now. So direct map. Well, we do have all the recorded lectures on the LMS. Those are recorded by me only. All right. Now, if it is a fully associative, the block of data can be placed in the cache anywhere. If it is set associative, the respective set is looked for using a formula, and in the set anywhere the data can be placed. In a direct map, what happens?
ma'am, a formula is used to
Yes, very good. So, and a formula is used to place the data. This placement happens when the cache is empty, and a replacement happens when the address did not match with the cache and there was a cache read miss, and the data was found from the next block of the memory, which is the main memory, and then the cache, because it was full, some block has to be replaced, and replacement happens depending upon what? The type of the cache. If it is a direct map cache, no policy is used. It is only the formula which is used to calculate the block number, and the respective block is replaced. While if it is a fully associative or a set associative cache, what do we do?
We use three replacement policies: random, least recently used, or first in first out.
Very good. And we have the FIFO. So I'll not discuss these in detail. This was read policies. A write policy, see, even if we are talking about any program, we might have out of 10 instructions, 9 are reads and only one is write, that writes the result. But still we do have writes in any program. So a write to the memory will obviously follow hierarchy again. So the first address goes to the cache, then to the main memory, and then to the virtual memory. If the address is found in the cache itself, the data is written there. And since cache is volatile also, and it is constantly getting updated, so you need to maintain a copy of this data into the next hierarchical level as well. And that is done using,
Two policies,
yeah,
mainly write through cache and write by cache.
very good. So we can have a write through cache, as the name says. So as the name says, the data is written in the cache and side by side in the main memory. So through, it's a through operation. While if I talk about a write back cache, this takes place with only the cache, and a block, or all the blocks which are written into the cache are written in one go in the main memory when any of the block is replaced. Write back is a little more efficient as compared to write through because it doesn't cause memory contention. Excuse me. Yeah. Now, this was the case of a write hit. What if a write miss happens? So the address has come, there is no matching with the cache. It cannot find the address in the cache, the write operation will not take place. What should happen next?
It will go to the main memory.
Right, very good. So it goes to the main memory and writes the data there. And then depending upon whether we are following,
Write, allocate, or no allocate.
very good. So no allocate. So we can have two policies here also. A write allocate says write to the main memory and create a copy in the cache side by side. While a write no allocate says write only in the main memory, do not write in the cache. Now, if there is a read miss for the cache, obviously the data will be looked for in the next hierarchical level, which is the main memory, and then a copy from there will be created into the cache automatically on a read miss. That's all for the basic concepts of cache. We did a few examples last time. We'll just move on to one more example and a particular case of an address mapping, how it takes place. So I'll just move on. ठीक है, यहाँ तक किसी को कोई डाउट तो नहीं है?
No, ma'am.
Good. I'll have to rub this off. So we've done this question. I'll just rub this off. Yeah. We've done this question on last Saturday and I explained it again in the last class. And then the next one, let's see. This one is a little particular. I'll take it a little later on. This one we did in the last class. We'll do one more today and then we'll move on to a specific example. All right. So let us just talk about this question. And so you all can just write down the question. Right. So in a 34-bit microprocessor with a 16 kilobyte cache, which is a direct mapped cache, and 64 byte blocks, how many bits of address will be required for the tag index and the offset? Now, anyone who can tell me what to do here? Okay. First question. Aaron will answer. In a direct mapped cache, how many blocks are there per one set? So in a direct mapped cache, okay, anyone else can also volunteer, there's no problem. In a direct mapped cache, how many blocks do we have per one set? Or we do not have any set?
One block per one.
Very good. Very good. Absolutely right. In a direct mapped cache, we have one block per one set. So as many number of blocks we will have the same number of sets, right? Okay. In a set associative cache, we are always given associativity. Say it is a four-way set associative cache or a 16-way set associative cache. That means we have 16 blocks per one set. And in a fully associative cache, we just have one set and all blocks as a part of that set. I hope that's clear.
Yes, ma'am.
All
Yes,
right.
ma'am.
All right. So let's start with this question. So this question says that your physical address, see, when it's given in a 34-bit microprocessor, it by default says that the word length is 34-bit, right? And uh, this one term is missing here, which it should mention that the address is also 34-bit. So right now the physical address which has come from the processor is a 34-bit in length. The physical address is given, the cache size is also given. It is a 16 kilobyte cache. And then it is a direct mapped cache. The block size is also given. It has 64 byte blocks. You just have to find the number of address bits in the tag, index, and the offset. So how will we go about it? Number one, point number one. What should be the first thing that we should find out?
Log offset.
Very good. So block offset is given at log base 2 of the block size. And the block size is right here. So it is log base 2 of 64, and that turns out to be 6 bits for the offset. Clear, everyone?
Yes, ma'am.
Yeah. Now, we should find the next step. See, we don't have any information about the tag. Now, the next step obviously comes that we have the total address. We have this much. I'll just draw this. So this much is given as 34 bits. 34 bits, right? This one we just found out, the offset. We just found out this one. Now, tag, there is no information about tag which is given to us. So the only option that we are left out with is find the set index. Now, set index says that it is log base 2 of number of sets in the cache. If it is a direct map cache, by default, it means that it has one block per one set. Am I right?
Yes, ma'am.
Yes.
Yes, ma'am.
So if it is one block per one set, we are given the cache size. We are given the block size. Can we not find the number of sets in the cache? Okay, I'll write it for you. So I have a room, and I know the dimensions of the room, and I know a table which is to be, I have to fill this room with tables, and I know the dimensions of the table. I will just divide the room size by the table size. I'll get how many tables will fit in, right?
Yes, ma'am.
On the same grounds, if I have the cache size, and if I divide it by the set size, I'll get how many sets are there. Now, the set size will obviously be your set associativity, which is number of blocks per one set, multiplied by your block size. For a direct map cache, what is the set associativity?
1.
Yeah, very good. So it's 2 raised to power 0, which is 1. And so I will have set size as 1 into your block size is how much? 64, 2 raised to the power 6. Yeah. Now, cache size is also given. It is a 16 kilobyte cache. So it will be 2 raised to the power 10 is 1K, 11 is 2K, 12 is 4K, 13 is 8K, and 14 is 16K. Correct?
Yes, ma'am.
Yes.
Yes, ma'am.
Okay. So we will just divide 2 raised to the power 14. So I'll just come to the solution. We wasted some time in joining now. Okay, so we have this 2 raised to the power 14 as the cache size. Associativity is 1, 2 raised to the power 6 is the block size. We get the number of set index bits as log base 2 of 2 raised to the power 8, which gives me 8 bits for the set index. Clear, everyone?
Yes, ma'am.
Okay. Now, see, out of 34 bits, we have 6 bits for the offset and we have 8 bits for the index. Obviously, Adding the two and subtracting from the total, we will get the number of tag bits. All right, should I move on?
Yes, ma'am.
Okay. Yes. So let's do a very typical example now. So I was telling you in the beginning that let us study the basics, and then we'll take up one example so that you understand all the concepts one by one. So we are given a question which says that you have an Alpha AXP 21064 microprocessor. This is the configuration which is given to us. That is found in the DEC 3000 model 800 workstation. So this is where it is actually applied, right? Now, your cache contains 8192 bytes of data. What is 8192 actually?
Cache
Cache size.
size.
Okay, in numerical value, what will 8192 refer to? When I say 1K, is it 1000?
1024.
No, ma'am.
Very good. So accordingly, 8192 turns out to be 8K. All right, this is always approximated. So this is 8K kilobytes of data which is available in the cache. And then it says 32 byte blocks. And what is this? 32 byte blocks.
Block size.
No.
Very good. So this is the block size with direct mapped placement. So all this data, the blocks which are available in the cache are available in a direct mapped configuration. Direct map means the processor will find out the formula and then find the block number in the cache, and the data will be placed at only that block number, nowhere else. Then it says it is a write through cache. So what is a write through cache now? For a write operation for the memory, obviously the first address will come to the cache. So whatever is written into the cache, it is written into the main memory side by side. Okay, and this has a 4 block write buffer. See, you might have consecutive write operations also happening, and for that this write buffer is given. So it is right now a 4 block. So you have the provision, the processor has a provision of writing 4 blocks into the buffer. Okay, and then it says write no write allocate on a write miss. So if the address is not found in the cache for a write operation, a no write allocate policy is followed. This says that the address will go to the main memory, write the data there, and will not write to the cache. Remember, everyone? Just now we revised everything.
Yes, ma'am.
Okay. Now, uh, okay. How much time is there? Okay. Yes. Now it says, let's trace the cache hit through a steps of hit as labeled in the figure. So this figure shows you how the address mapping takes place and what happens on a cache read hit. Right? Step number 1, the physical address, which is right now, uh, it's not given. Hmm, it's not given. I guess this should be 32 bits. It's not given, but Alpha AXP microprocessor, I guess, is 32 bits. Let's see how much does it add out to. Yeah, 34. This is 34 bits. Let's write it here. So this total is given as 34 bit now. Right? Now, this is by chance that it is not mentioned here. Otherwise, if any processor's configuration is given, whatever is the address length will be mentioned to you. Don't worry. All right. Now, this 34-bit address which has come from the processor goes to the first hierarchy level in the memory, which is cache. And with the cache, first of all, the cache has its own addressing. It has its own tag, index, and offset. The address that has come also gets dissociated into 3 parts: the tag, the index, and the offset. Just hold on, I'm getting a call from the office. मनोज जी मेरी क्लास चल रही है, मैं बाद में कॉल करती हूँ. All right. Yes, so what was I saying? Yeah, so the address that has come from the processor gets dissociated into three parts. So we have the first thing that happens is the offset, right? Anyone who will tell me what is the offset here? Am I audible?
Yes, ma'am.
हाँ, मुझे acknowledge करते रहा करो because you know I feel that the signal is gone off.
5 bits.
5.
Yeah. Yeah. So log base 2 of the block size, it is 5 bits right now. And how many, because we just did an example of a direct map cache, same applies here. So you have 8k divided by 2 raised to the power 5. 2 raised to the power 13 divided by 2 raised to the power 5. How many bits you get?
2 raised to the power 8,
Yeah.
8 on.
Yeah, so log base 2 of 2 raised to the power 8, we get 8 bits for the index, and remaining obviously has to be the tag. So 21 bits for the tag, 8 bits for the index, and 5 bits for the offset. Yes, step number 2, the address mapping starts taking place. The first thing that maps is to locate the respective set number. So after the set is located, so the index bits start mapping with the available index bits of the cache. And after the matching takes place, the next step is obviously to find the
I'm sorry, can you repeat what you said?
My question is, पहले तो हम सबसे पहले सेट लोकेट करेंगे, है ना? सेट लोकेट हो गया, उसके बाद हम क्या लोकेट करेंगे?
Valid bit.
हाँ, तो उसके बाद हमने पहले तो ब्लॉक फाइंड आउट करना है, पर ब्लॉक से पहले हमें क्या फाइंड करना है? वैलिड बिट. सो वन मोर थिंग, ऑल द टैग्स मैप इन द पैरेलल. ये हमेशा पैरेलल में होती है टैग की मैपिंग. तो ऑल द टैग्स आर चेक्ड इन पैरेलल. सबसे पहले टैग चेक होने से पहले भी वैलिड बिट्स चेक होती है. सो even if the set is located and the valid bit is 0 for a respective tag, the next mapping does not happen, right? And if suppose the valid bit right now is 1, it is not 0, the cache contains some data, the next thing that happens is the mapping of the tag, right? And after, see if you can see this arrow, after the valid bit is 1 and the respective tag is located, the next job is to, in a block, will you have just one byte or one word of data?
No, ma'am.
Yes, we can have more, more number of words of data in any data block in the cache. तो सब तो नहीं चाहिए होते ना इन वन गो, तो प्रोसेसर अपनी वर्ड लेंथ के हिसाब से ही उठा पाएगा. इफ इट इज एक्सेसिंग डेटा, if the processor is a 32-bit processor, by default it can only access 32-bit in one go. At the most 64 if it is it's a double precision operation. Are you getting my point?
I'm थोड़ा
थोड़ा मैं फिर से बताती हूँ. एक मिनट, मैं ना चार्जर लगा लूँ, मेरा लैपटॉप बंद होने वाला है. जस्ट अ मिनट, जस्ट होल्ड ऑन फॉर अ मिनट. Yes. So what I was saying was that I'll just draw it for you. So we have this processor and we have this cache. Just use some other color. So we have the CPU and then we have the cache, right? This cache is a direct mapped cache, and then we have lots of blocks here. The size of each block is minimum 4 bytes. So I can write greater than 4 bytes. Huh? This is better. Yeah. Now, so the size of each block is minimum 4 bytes and can be greater depending upon the maximum size of the cache. Right. Now, any address that has come from the processor, first of all, maps the set index. So it's found this set, and one set has one block. Obviously, it has found one block actually. Getting? Are you all getting?
Yes, ma'am.
Yes, ma'am.
Yes. Now, in this block, the next thing that should map is the tag. But before the tag, the valid bits are all checked. If the respective tag, even if it is matched and the valid bit is 0, the next mapping does not take place. That by default means that the block is empty. There is no need to go for that mapping. There's no need to waste time in that address mapping. Now, after suppose the valid bit is also 1, and this block, so this is the block which is located. So if I'll just take this one. So this is the block which is located now. The block size is minimum 4 bytes and it can be greater also. 16 bytes, 32 bytes, 64 bytes, 128 bytes, 256 bytes also. Right? Now, if the processor is a, what do I mean by a word length?
The total number of bits the processor can process in one go.
Very good. So right now we are talking about DLX, which is a 32-bit processor. We do have 64-bit processors also. If you all know, I guess the recent systems which are there in the market are all 64-bit. है ना? हम
Yes.
जितने भी
Yes, ma'am.
recent risk based processors खरीदते हैं वो सब 64-bit होते हैं. Now suppose it is 64-bit also or maybe 32-bit. In one go, the processor needs from the entire block either a 32-bit data or a 64-bit data, right?
Yes, ma'am.
It does not need the entire block. It cannot operate on the entire block. So if we have to find from the entire block just a part of the data, so maybe this much, right? The offset is then concatenated along. What do I need? What do I mean by concatenation? Anyone?
Concatenation means कि उसके आगे लगा देना,
हाँ,
like if
बिल्कुल
32 bits are from yes ma'am.
बिल्कुल suffix की तरह ऐड कर देना है ना. Very good. So the first thing that happened was the location of the set. So this set was located and it is a direct map cache, so it is one block per one set. And then after checking the valid bit, if it is 1, and then the tag also maps, the respective block of the data is accessed, right? Now this block can be minimum 4 bytes and greater also. And if it is greater, obviously it contains a large chunk of data, while we need only a part of that chunk. So all the data is brought into a mux. A mux is a multiple input, single output unit. We all know that, right? Now see, the offset, if you can see the pointer, is brought in here. It is concatenated along the required address to find the correct location in the respective block, correct data location in the respective block. जैसे, I'll give you one example. Suppose हमारा offset था फिलहाल 00 से 100, राइट? अब यहाँ पर ये वाला जो ब्लॉक हमारा लोकेट हुआ है, इस ब्लॉक में I will have many combinations of the addresses for each chunk of data, है ना? Suppose it is right now one block is how much it is saying? It says it is a 32 byte block है ये. 32 bytes का एक ब्लॉक है और हमें कितने चाहिए? 4 bytes चाहिए सिर्फ. Fine? Are you all getting?
Yes.
Yeah.
Yes ma'am.
Address is concatenated with the given address. ये वाला मैप हो गया, ये वाला भी मैप हो गया. अब इसके आगे इसको लगा दिया जाता है और जहां पे लास्ट वाली बिट्स मैप कर जाती हैं वो वाला डेटा मग से आउटपुट ले लिया जाता है. सो यू नो, if I talk about, say, if it is a 4:1 mux, it can have 4 combinations right now, 2 to the power 4 combinations. 4 zeros to 4 ones. Getting?
Yes.
Yes.
So it can have these 4 combination. जहां पर भी उसका concatenated वाला address map होगा वो वाला output select कर लिया जाता. So we select that output, and that is the data which is put on the data bus and brought inside the central processing unit. If anybody has any doubt till here, you can ask me. I hope it's clear. Okay, very good. Now, so this was a perfect case of how address mapping takes place. When the address comes from the processor, how it is dissociated based upon what formula, how the address mapping takes place, and finally how the data is accessed by the CPU, right? And then this was only the case of a read. Write operation I will take in the coming lectures. Right now I have to start with another topic. I have how much time? I have 5-7 minutes. In the meanwhile, if anybody has a doubt, can ask. Yes. So while we were doing these data hazards, we talked about hazards which are, where is the marker gone? Yeah, there it is. We talked about hazards which are of the type, ये कब होते हैं? Excuse me. When do these happen?
These are kind of data hazards.
Mm-hmm.
So they happen when there is a clash in the memory, like whenever the data is written before reading or is read before writing it, like
Okay, good.
war in.
Yeah, very right. When we talk about the data hazards of the type war and WAW, what actually happens is that if we have two instructions, say I succeeded by J, right? The I instruction might be a memory access, and while accessing the memory, there is a cache miss or there is a main memory miss. So the first instruction is still stuck on to the memory access part while the next instruction moves on. And then such a case leads to a war or a WAW hazard. Getting?
Yes, ma'am.
Yes, ma'am.
Now, that time I told you that, we have memory misses. And this is what we have to discuss today. So what is a memory miss and what is a memory miss penalty? That we have to start today. Next time I'll, take this in detail. थोड़ा सा आज brush up करा लेते हैं. इसका prerequisite पढ़ लेते हैं. Now, see, we all know that we have, right now, we talked about 4 levels of memory. Registers, which are internal to the CPU, followed by cache, followed by main memory, followed by your disk storage, hard drive. And then their sizes are also mentioned. So registers would be sometimes, less than 1 kilobytes, and cache would be, these are just, old values. Current values will be much higher. If you talk about the current market, which is, dealing with computers and their hardware, so it will be much higher right now. A cache was typically less than 4 megabytes. Main memory less than 4 GB. What is the size of main memory right now? कितना आ रहा है आजकल?
1 TB.
1 TB, 2 TB.
Yeah, it is 1 terabyte. Yeah, it is there. But then they have those solid state devices also, which they are including in between. Yes, and then followed by your hard drive. And then implementation technology, we already know cache is static RAM, main memory is dynamic RAM, and your disk storage can be magnetic disk. It's not necessary every time, but it can be magnetic disk. And your registers are either CMOS or BiCMOS. And accordingly, their access times, their bandwidth, which is the data access per second, which is possible. And finally, who is the responsible, who's taking the responsibility of dealing with these hardware devices. So registers are held with the compiler. Cache is respectively taken care of as a hardware unit. Main memory is taken care of by the operating system, and your hard drive also, either by the operating system or manually also we can do it. And then every level is respectively backed by the next lower hierarchical level in the memory. So cache is backed by main memory backed by disk, and definitely We have your disk, which is backed by your we have the external, we connect the flash devices, and we have the magnetic tapes. Now, why I discussed all this is the point that any address that comes from the processor will first of all go to the first hierarchical level in the memory. And if the data or address is not found there, it's a miss. And then some clock cycles have already been wasted in accessing the data from here. The address goes to the next hierarchical level and maybe gets the data or the instruction from here. If you can see my cursor, it gets it from here. But these number of clock cycles which are wasted are an overhead to the pipeline. See, we are trying to optimize the processor speed. I hope there is some time. Yeah, I do have. So we are trying to optimize the processor speed. And for this optimization, we discussed a few techniques last time. We talked about parallelism within instructions. We talked about optimizing the memory hierarchy. Then we talked about multiple processors. Then we have, there was one more. We can have, multi-core processors also we can have. There was one more which I said in the classes earlier. I cannot recall right now. Multi-threading. Yeah, so we can have multi-threading as well. So lots of techniques which are there, right? Now, apart from pipelining, if we are, adding on to the processor speed by memory hierarchy, following memory hierarchy, and in the memory only there is the miss. This causes a few clock cycles to be wasted. These clock cycles are also an overhead to the pipeline, and they have to be accounted for while calculating the processor speed or its performance. Getting everyone?
Yes, ma'am.
Right. So the way we used to calculate an overhead for the pipeline, now we have to calculate the overhead because of memory misses. This we will do in the next lecture and the respective numericals, and then we will start with main memory and virtual memory. That's all for today. And अगर आगे से 5 मिनट तक ज्वाइन ना हो तो रिया मुझे कॉल कर लिया करो, because I had started teaching without even realizing that the students have not joined.
Okay, ma'am.
ठीक है बच्चे, चलो, okay, thank you for today and we'll meet again on Saturday.